Now we come to the trend in melting and boiling temperatures. We will see that when we compare lithium, beryllium, we will see that both lithium and beryllium have metallic structure, giant metallic lattice, and the type of bonding is metallic. We will see that the melting point of beryllium will be higher than the melting point of, or the melting temperature of lithium. Of course, the boiling temperatures and melting temperatures are related. So if the melting temperature of beryllium is higher than that of lithium, so the boiling point or the boiling temperature also is higher than that of lithium. Now, why does beryllium have a higher melting point than lithium? Now, we say that both are metals. They are both metals. If we compare lithium with beryllium, so both are metals, we'll see that in case of lithium, the metallic bond is formed by the removal of an electron from the outermost shell. It is not removed, but the electrons, the outer shells merge together. The outer shells merge together, and the lithium metallic bond will consist of a lattice of +1 charge, and each lithium left an electron that is moving in between the layers of the positive ions. And so the attraction force between the positive nuclei and the electrons that are present in between the layers, we say that in the metallic bonding, of course, we are going to study about metallic bonding later. So if you look here, in case of lithium, you will see that each lithium will consist of, the metallic bonding consists of a lattice of positive ions separated by a sea of electrons. And due to the attraction force between the positive nuclei in the lattice and the electrons that are moving, we get the metallic bond. In case of beryllium, beryllium is present in group 2. And so we will see that 2 electrons leave the nuclei, leave the atoms, and we have +2 lattice, a lattice consisting of +2 ions, and each atom left 2 electrons. Here we have 2 electrons coming out from every atom. We have 2 electrons coming out. And so the number of electrons and the number of positive charge is greater than that in case of lithium. When we have more positive charge and we have more number of electrons, the attraction force in case of beryllium will be greater than the attraction force between the positive lattice and the electrons in lithium. And since the attraction force is greater, this means that it has a higher melting temperature than that in lithium. Here we have +2 charge, and we have each atom left 2 electrons to be moving in between the layers. So the attraction force between a +2 and 2 more number of electrons, of course, the electrons are moving, not only +2 attracting +2 electrons, no. All the positive lattice attracts all the electrons that are moving in between the layers. The attraction force here will be greater than that in case of lithium. That's why we see that the melting temperature in case of group 2 is greater than the melting temperature in case of group 1. It's greater. Now, when we look to boron, which comes after them, boron is not a metal. Boron, if you look at the type of bonding in case of boron, we'll see that boron has a giant covalent structure. It resembles the structure of diamond. Each boron is bonded to 4 other boron atoms in a giant covalent structure. We have here a giant covalent structure, and we will see that the melting temperature of boron is greater than the melting temperature of both lithium and beryllium because it has a giant covalent structure. It has thousands of covalent bonds, and all these covalent bonds are strong bonds, and it requires a big amount of energy to break all these strong covalent bonds in order to melt the boron. So the melting temperature of boron will be greater than that of beryllium and lithium because boron has a giant covalent structure, and so it requires a big amount of energy in order to break all these strong covalent bonds in between the boron atoms. Requires a big amount of energy. That's why the melting temperature here will be greater than that of beryllium and boron. So you will find here that boron will have a higher melting temperature than that of beryllium and lithium, and also diamond. Diamond, we know also that diamond is a giant covalent, has a giant covalent structure, and so each carbon is bonded to 4 other carbon atoms in a tetrahedral structure, but we have a giant molecular structure. We have a giant molecular structure. We have thousands of carbon-carbon covalent bonds that requires a lot of energy in order to be broken. So diamond has the highest in group 4. It has the highest melting and boiling temperatures compared to all the other elements. But when we come to nitrogen, oxygen, and fluorine, these are simple covalent molecules. They are simple covalent molecules because we know that nitrogen consists of N2. It is N triple bond N, as we are going to study in covalent bonding. And when nitrogen is bonded to another nitrogen, it is bonded by weak forces. Of course, we are going to study about these weak forces in Unit 2, but here we're just going to say that between nitrogen and another nitrogen, there is a weak forces of attraction. Also between oxygen and another oxygen, we have weak forces. Between fluorine and another fluorine molecule, we have weak forces of attraction. That's why we will find that the melting temperatures and boiling temperatures are so low. If you compare nitrogen to oxygen to fluorine, we will see that all of them have weak forces between their molecules, and so they have the least melting and boiling temperatures. They consist of simple molecular, they have simple molecular structure. The same will be found in period 3. We have sodium present in group 1 and magnesium present in group 2, but here also aluminium is a metal, but boron here was not a metal, but aluminium is a metal. And all these 3 metals have metallic bonding and they have giant lattices. As we said that whenever in case of group 2, they leave 2 electrons and there will be attraction force between a +2 lattice with more number of electrons. In case of aluminium, we will have a +3 lattice. In case of aluminium, we have a +3 lattice, and each aluminium leaves 3 electrons in between the layers. And so there will be a stronger attraction force between the greater number of electrons and the positive and the greater positive charge. And so due to this stronger attraction force between the positive lattice and more number of electrons, we will find that aluminium will have a higher melting temperature than magnesium, and magnesium higher than sodium. And since silicon, like carbon, has the giant covalent structure, where each silicon is bonded to 4 other silicon atoms in a tetrahedral structure, but it is a giant covalent lattice, we need or require a very big amount of energy to break these strong covalent bonds. That's why silicon also has a higher melting temperature than that of aluminium or magnesium or sodium. But if we look at phosphorus, sulfur, and chlorine, we'll find that these are simple molecular, they have simple molecular structures. They are bonded together by covalent bonds, but they are simple molecular compounds or molecules. And so since we have simple, like in case of nitrogen, oxygen, and fluorine, since phosphorus, sulfur, and chlorine are also simple, then we will see that it requires less amount of energy to break these weak forces between the molecules. But of course, as you see here, in case of phosphorus and sulfur, they have higher melting temperature than that of chlorine. That's because we know that in phosphorus, we have the phosphorus element is P4, and in case of sulfur, it is S8, but in case of chlorine, it's only Cl2. we'll see that the more the number of electrons, the higher will be the stronger will be the intermolecular forces of attraction, and that's why sulfur has the highest melting temperature. That's because it contains 8 sulfur atoms bonded together. Its molecular formula is greater. Its molecular mass, sorry, is greater. It has greater number of electrons. The more the number of electrons, the stronger is the weak forces between the molecules. So between an S8 and another S8 molecule, there are stronger forces than between P4 and P4. That's because sulfur has more number of electrons. So the weak intermolecular forces between sulfur is stronger than that between phosphorus. That's why it requires more amount of energy to break between S8 and another S8 molecule than to break between a phosphorus and another phosphorus molecule. And of course, since chlorine contains only 2 atoms of chlorine, so the number of electrons here is smaller than the number of electrons in case of phosphorus or in case of sulfur. And the attraction force between 2 chlorine molecules will be the weakest, and it will require the less amount or the least amount of energy to be broken. Of course, we are going to study about these forces of attraction, these weak forces of attraction in Unit 2, inshallah.